Earlier, we talked about Lewis acids and Lewis bases and how they can come together to make adducts. Well, most of the time in a Lewis acid, Lewis base system, there's often a transition metal acting as a Lewis acid, and then the Lewis bases, which are different kind of either ions or compounds with lone pairs, will be Lewis bases. And the Lewis base electrons push themselves into one of the empty orbitals of the Lewis acid to make a complex ion. So transition metals are great at forming these complex ions. All right, they're great Lewis acids, and Lewis bases can be things like cyanide and ammonia, which are shown here. It could also be water or even just chloride. It's hard to say, but they're really great about taking them on. And when this happens, you end up with incredible colors. So down in the lower right, you can see different combinations of metal ions with water, and water has two lone pairs on the oxygen, so it's a great Lewis base. But anyway, the colors are just fantastic. The first one there is the scantium, which has no color, but then chromium 3+, cobalt 2+, etc., etc. So it's kind of cool and stuff to see the different things. In this chapter, Lewis bases we're going to call ligands. Ligand is just a fancy name for a Lewis base. And when it comes to coordination chemistry, Lewis bases are usually referred to as ligands. So it's pretty cool how this all works out. Those two examples with iron and nickel on the product side are both complex ions because they have a charge. All right. If you had just a complex or complex compound, you would just have a neutral charge, and we'll see this here in a little bit. So complex just means you have a central metal ion that's bonded to one or more molecules or ions, one or more ligands. The Lewis acid is always going to be the metal in this chain, and that's the center of the coordination, if you will. And those Lewis bases or ligands are just molecules or ions. They're covalently bonded to the metal in the complex. And a lot of the colors of transition metals are the results of these ligands connecting to the metals. Water itself binds to all the transition metals really well, like in that picture in the lower right there, and that's where a lot of the colors come from. A coordination compound will have one or more complexes, one or more complex ions. So these are just different examples there that are showing. Now in the first example, you have a cation, which is that thing in square brackets, with some chlorides. In the second example, you have a cation, which is the copper part, and an anion, which is the platinum part. And in the third example, you really don't have a cation or an anion, but you certainly have a complex because the platinum is a Lewis acid. It's being surrounded, if you will, by the two ammonias and the two chlorines. So these are all examples of coordination compounds. They're neutral. They don't have a positive or a negative charge. The coordination number of a molecule depends on what's bonding to it, all right? And a lot of times the coordination number will be 6. So in the upper right-hand corner there's an example of a cobalt compound with 6 ammonias around it. And you can see how each of those nitrogens on the ammonia, which has a lone pair, is pushing essentially its lone pairs into the empty orbitals of the cobalt, making the Lewis acid, Lewis base interactions. And since there's 6 ammonias around cobalt, we would say the coordination number is 6. You can also, though, have coordination numbers of 4. This is a platinum compound. This platinum has 4 Cls around it, and Cl has lone pairs as well. They're each pushing their lone pairs in. That would be a coordination number of 4. The most common coordination numbers are 6, 4, and 2. Again, it kind of varies and stuff depending on which one you have. It kind of depends on the metal too, and we don't need to worry about why some make 6, 4, or 2. But anyway, the coordination number is determined by the ligands, by the Lewis bases that are around those Lewis acids. And there's lots and lots of examples of them, and we'll go through some of them here in a little bit. Coordination number 2, when you have this, it usually results in a linear geometry. And there's a few of these out there. One we've talked about a little bit before is what is the silver ion with a couple of ammonias around it. Now, ammonia is the Lewis base, silver is the Lewis acid, and they bond pretty readily to make that complex ion. So in that little picture there, the light blue in the middle, that would be the silver, and then the darker blue on the outside, that would be probably the nitrogen on the ammonia, pushing its electrons inside. But these will result in linear geometry, so the angles would be about 180, all that kind of stuff. Coordination number 4 is definitely happening. You can have a tetrahedral arrangement, which does happen quite a bit. And you can see in those examples down there, that would be zinc with 4 ammonias. So each of the reds would be an ammonia, and the light blue in the middle would be a zinc, for example. But you can also have square planar. Square planar molecules have usually a transition middle in the center, and then 4 Lewis bases around it. Now, square planar things usually have lone pairs on the central atom, and that's more than we need to talk about in this class, but just realize you do see sometimes these 4 coordinate square planar as well as 4 coordinate tetrahedral compounds. Coordination number 6 is probably the most common, though, of all, and this makes an octahedral geometry. When we talked about Lewis structures in Vesper, we saw some octahedral compounds. We're going to see a lot of octahedral compounds in this section. So again, octahedral in this context means you have 6 points where the Lewis bases are interacting with the metal center. And so that means you can have, for example, 6 different ligands, like 6 cyanides. But notice here the next compound, there's only 3 of this En thing. Some compounds can bind in more than one place, and I'll show you examples of that here in a little bit. So there's lots of examples. At the beginning of Chem 222, we looked at the FeSCN2 plus molecule, and FeSCN2 plus is actually an iron with a thiocyanide, which you probably knew, but there's also 5 waters around it too. So it's an octahedral iron compound where the SCN minus is kicking out one of the waters in an equilibrium. And we found the equilibrium constant, all that jazz looks kind of blood red. Well, here we are back and stuff. That's what we're going to look at. Pretty cool stuff. Now, the charges on coordination chemistry species deserves a little bit of comment. The charge of a complex ion is equal to the sum of the charges on the metal and the ligands. And I'll show you an example of that down there with the FeCN6-3 compound. However, on the right-hand side is an example of a coordination compound, and the charge on that will be the sum of all charges on the metal ligands and any kind of counterbalancing ions that you might have. So let's look at the FeCN6-3 compound first. Let's say we wanted to find, for example, the charge on the iron. Well, cyanide, Cn, is always a -1, and there's 6 of them. So if you just thought about the 6 -1 cyanides, you'd think you'd have a -6. But as you can see, that's a -3 overall charge. Like the little number outside the square brackets is -3. So if the cyanides are -6, but the overall charge is -3, something must be giving a +3. And you guessed it, that's the iron. So this is an iron Roman numeral 3 or iron +3 compound right here. And those 6 cyanides, which give -6, are being balanced a little bit by +3. So the overall complex has a -3 charge. Because it's negative, this is an anion, so it's an anionic complex. If the overall charge was positive, you could have a cationic complex. On the right-hand side, there's a part in square brackets with the cobalt, but there's also 2 Cls on the outside. The Cls on the outside are called counterbalancing ions. So let's first of all figure out what the charge would be on the inside part, the part in the square brackets. Well, ammonia is neutral, all right? So those 6 ammonias don't contribute to the charge at all. And it would be hard at this point to find the charge on the cobalt. But there's 2 Cls. And they are counterbalancing any charges that happen in the complex ion, the parts inside the square brackets. So because chloride is -1 and there's 2 of them, and because ammonia is neutral, and the whole complex is neutral for that matter, that cobalt must be a +2, because that will balance the 2 -1 chlorides on the outside, those counterbalancing ions. Ammonia has no charge. This is an overall neutral compound. So one thing that's going to be important is that you can find the charges on the metals in the middle. And sometimes they're a little disguised, but if you know all the polyatomic ions and stuff like that, you'll be good to go. Chloride's always -1, cyanide's always -1 as well as hydroxide, stuff like that. But water and ammonia and things like that will be neutral. And overall, then you can figure out what the charge will be on the metal. So here's a question you might see. It says, what is the charge on the copper atom in this CuNH32Cl2 compound? All right, no problem. Well, once again, ammonia is neutral. It has no charge. It doesn't have any positive or negative, so we can ignore it essentially. We have copper, but we don't know what its charge is. But we also have two chlorides. And remember, chloride, like bromide and iodide and all those, -1. So 2 times -1 would be -2, but the overall compound doesn't have a charge. Like there's no positives or negatives in that thing. So that means this copper must be a +2. It's a +2 because it balances the two -1 chlorides. Ammonia is neutral. This is a copper 2+ compound, which is kind of cool.